My kitty joins us again today to help us learn some math. So I'm looking forward to your questions, and so is my kitty Squeaky. Say hi, Squeaky. Say hi to everyone. So let's see what we have going on today. I guess it's the latest activity 16, I believe. And when we finish up activity 16, we will start on the next stuff. That video will be out probably maybe tomorrow or so. We do have spring break week coming up, so that'll slow us down a little bit as far as getting the progress done. And then let's see, so Tuesday after spring break, we will cover, I guess that'll be activity 17, and then we will take the first exam on that Thursday during class time. So today, let's see, I guess before class today, the most previous activity, I guess that was activity 15. Activity 15 was due. It looked like my inbox was pretty full this morning. I'm going to spend some time tomorrow and the next day trying to get all my grading caught up. This week, I thought I'd be able to keep up pretty well with everything, but I open up my inbox in the morning and I get 20 to 25 emails from administrators asking me how things are going, offering me this suggestion, that suggestion, telling me this, telling me that. I'm trying to make everything work as smoothly for everyone as I can. It seems like this is going pretty well. If you have any comments or things that could make this go better, I'm certainly willing to listen to them. I really like the way that this platform has been working. I know others use different ones, but there have been issues with connectivity for all the students, and there have been issues with the streams getting a little too full. So I'm happy with the way this is going. If you have any other suggestions, feel free to let me know via email or even in the comment section. So right now I'm waiting for my first question. Chat something to me. Let me know what's on your mind, what I can help you with today. Question 7, activity 16. Sure thing, Drew. So what I'm going to do to help you get the equation set up that needs maximizing is I'm going to first off on the left-hand side of the board, go through sort of part A, and then on the right side of the board, I'm going to go with part C and show you sort of how those things fit together. So on part A, we determine that this length right here is 100. On part C, we just decided to call this length X. I'm pretty sure these were yards. Yeah, yards, okay. We have a total constraint of 500 yards. So that's all the material that we have left to build the fence. And we're also constraining ourselves to this particular shape with that rock wall. I'm saving us 50 yards of fencing so we can enclose a little bit more. So if I were to say this is 50 and this is 100 and sort of go through everything, I should be able to put numbers on all of those. If that's 50 and that's 100, that's going to make this side be 150 long. So tell me what length this side would have to be, knowing that this side is 50 and that side is x. I should be able to come up with an expression for that right there. Sure, Sarah, I'll go over 1a as soon as we're done with this. So let me know, what should this length be of the rectangle? Sort of scouting out what we did with the numbers we knew versus the numbers we don't know. Yeah, x plus 50 is exactly right. Back to this first half now. If we've used up 150 yards here and 100 yards here, so far we have used 250 yards. How about in this case? If we have x yards of fence there and another x plus 50 yards of fence there, what's the total amount of yards of fence that we've used to build this short stubby wall and then this long one? What would that expression be using algebra? 2x plus 50 is exactly right. So we've used 2x plus 50. Okay, so if we've used 2x plus 50, in this case, we've used 250. In this case, there was how many to start with? 500. So this is how much left. So the amount left is going to be 500 minus 250, which leaves us the remaining. Yeah, okay, yeah. That, which is exactly 250. Now, with that 250, I have to build two fences, and those fences are exactly the same size. So I'll take, for each side, I'd have to take that 250 and divide it by 2. So that would be 125, and that would be 125. So I have this first case all taken care of. I'm going to add up my sides, make sure they add up to 500. 150, 250, those two are 250 more. Sure enough, that's 500. I feel really good about this one. And then the area, of course, that's what I'm trying to maximize. I could calculate the area. The area here would be whatever 150 times 125 is. You can calculate that on your own. So you can probably figure out where I'm going on this case we didn't know. Used, that much. Left over. Well, we started with 500, we used that much. We'll do the same sort of calculation here. We started with 500, we're going to subtract off the 2x plus 50 that we've used. So do that subtraction carefully, and if you do that subtraction carefully, you have to remember to distribute the minus sign. If you distribute the minus and do the subtraction, what's left? $450 minus 2x is exactly right. So there's 450 minus 2x yards of fence left, but that has to, of course, build both this side and this side, both those sides being even. Now, last time we had 250 left, what did we do to figure out the length of each side? Well, divided by 2. We'll do, of course, the same thing here. We'll divide this amount left, divide the whole thing by 2. And since we're dividing by 2, I can do each of those two independently, since 2 is a monomial. I could take the 450 divided by 2. That's 225. And I can take the 2x divided by 2, and that is x. So each of those two other sides, 225 minus x, should be that long. Now here's another way that I'm going to make sure that, there's two ways really that I'm going to check to make sure that this makes sense. I know when I added all those pieces up, it should be 500, so let's do it. If I add this plus this, that's 225. If I add this, that's 450 minus x plus x is 450, plus 50 is 50. So if you add this plus this plus this plus this, using some basic algebra and adding like terms, Sure enough, that's equal to 500. So I feel really positive about this being right. The next thing I'm going to do to make sure that everything aligns beautifully is I'm going to allow x to be 100. And if I do, I should be able to generate this 150 and those two 125s. So substituting 50 in there, I'm sorry, substituting 100 in for here, this is 125, that's 125, and that's 150. So when x is equal to 100, I get exactly the same numbers on all those pieces. And then I know that I have it right. So let's see, we want to maximize the area. The area is length times width, so the area function will have to be x plus 50 times 225 minus x. There's the area function. Is there anyone in the group out there that wants to see me carry out the calculus and the algebra to actually maximize that function? That's just sort of one we've been doing. You know, we did quite a bit of those on the last activity. Again, the really nice thing about working this first through with numbers that you know is that when it comes time to work with numbers that you don't know, in other words, to work with variables, you have this sort of idea, what was the thought process that you went through with the numbers you knew? Use that exact same thought process with the numbers that you don't know, okay? Well, what is the domain of the function? Excellent question. Well, the smallest x could be would be 0, right? We don't have to have any x there whatsoever. But we also can't let x be 1,000,000 because we don't have enough fence. So these two sides, the two lengths, have to be, if you add those together, the x plus 50, that has to be less than the total amount of fence that we have. Because if we use more than that for those two pieces, there's nothing left to build those two side pieces. So those two sides, this plus this, have to use up less than the 500. 2x has to be less than 450. X has to be less than 225. If I make this 225, that makes this be 275, and there's no fence left to give this the second dimension at all. So let's see, the dimensions would be, I guess I could use 0, so I'm going to put a solid bracket around 0, and then 225. I must use less than 225, otherwise the area is nothing. I could let this side be 0 and then just build the whole thing out, letting this side be 50 and letting the other sides be 275, I guess. X is 87.5. That seems to ring a bell, yeah. And I recall this one ended up being a square. So if this is 87.5, that makes this one 137.5. 80 off of there. That's yeah. But that seems to ring a bell. I'm not precisely sure. Yeah, I'll work it out just to make extra sure. Foil this out. 225x plus 50 times 225, that's 0. 25, carry the 2, 10, 12, carry the 1, 11, 250, minus x squared minus 50x. That appears to me to be the product of those two. Let me put it in a little more concrete form. 11, 250 plus 175x minus x squared. There's my a function. A prime would be 175 minus 2x. And if I set that equal to 0 to find the critical point, sure enough, 87.5 is exactly right. Okay, so now that we know that that's 87.5, we can say what the length of that is. 87.5 plus 50. The length of this rectangle is 137. Is that right? 85 plus 87.5, 137.5. And if I allow x to equal 85, 225 minus 85, or minus 87.5. I think if you subtract that off, you probably get the same 137.5. Yes, you do. Yeah. So that comes out to be a square. Here's my second derivative test. A double prime in all cases here is -2. And since the second derivative came out negative, that means this graph is always concave down. And since it's always concave down, I have indeed found a minimum at my one and only critical point right there at 87.5. Got it. Yep. So everything is, is pretty well settled on that one, showing the algebra and showing the calculus. And I guess I did have one, I didn't get to look at every single activity 15 that was turned in, but I did notice a few people sort of left out some of these details in the middle as if they were unsure as to where to proceed. Make sure you can do the calculus and the algebra, starting with the basic multiplication of binomials, gathering like terms, then the first derivative and second derivative fly from that. Okay, Sarah, you wanted me to look at number 1 on activity 16. Sure, I'll go back and see if I can find that one. Yeah. So on problem 1, I wanted to reinforce the idea of the second derivative test. Now there's scant information given on either 1A or 1B. I don't know any points, any place on the graph. The only thing that I know is I have the first derivative at 20 is equal to 0. Let's see if I can find my scale. It looks like 20 is right about in the middle there. So I know when x is equal to 20, the graph is absolutely flat. I have no idea how high or how low that point is, but I have a critical point right there at 20. And also at 20, I notice that the second derivative is positive. And since the second derivative is positive, that tells me I have a graph that's concave up. So I'm going to draw a graph that's concave up right around at 20 and also has a critical point at 20. So here I go. So at x equal to 20, the graph has a first derivative of 0. The graph is also concave up. And at 20, therefore, I have what? A relative min. The function never drops below 20 in the vicinity. I'm sorry, the function never drops below this value in the vicinity of the number 20. Same thing then on problem letter B. I have the first derivative is equal to 0 and x equal to 8. I don't know any value at all for the function, so I'm really free to draw this as high or as low as I wish. I do know that the first derivative is 0, which tells me I have a critical point, a place where the slope is 0. And right around the number 8, I have the second derivative being negative, so I have a graph that's concave down. So maybe the graph looks something like this. Who knows what happens afterward? But right there at 8, I have a critical point. The slope is 0. And right there at 8, I have a graph that's concave down. So I have a relative maximum value right there. So at x equal 8, I have a relative maximum value. That's the second derivative test. If you have a critical point and the graph is concave down, second derivative negative, you found a relative max. If, like I had on the previous screen, if you have a first derivative that's equal to 0 and the second derivative is positive, you have a graph that's concave up and you found a relative min. Now, I don't know for sure if that's the absolute value or maximum value that function takes. Who knows what happens after that? But right in that area, right around the number 8, I've absolute maximum value. So that's problem number 1. I guess I did more than I asked. Sorry about that, Sarah. I probably should have left you figure out part B. So we have 1 out of the way and 7 covered. I think I covered it in its entirety, didn't I? Everything except for part B. Yep. And I guess the summary on part 7, I didn't figure out exactly how much fencing, or exactly what the square root was. Well, I always get questions about when these are due. These are always due right before the next class begins. So our next official class is after spring break. Hope you all have a safe spring break. I know that these circumstances certainly have messed with a lot of people's travel plans, including my own. But we're doing what we have to do here. If you have a few extra minutes, spend learning your calculus. That's probably not the worst thing in the world. Go over question 6. Sure, I'll go over question 6 now. As soon as I find it. There we go. Yeah, question 6 is by far the most time-consuming on these. But once you catch on to how these problems work, they're a bit formulaic. There's 2 main things. There's a storage cost and then some sort of either manufacturing cost or an order cost. That order cost tends to be a reciprocal function, and the storage cost tends to be a linear function. And really, there are scant numbers in any of these problems. And once you see how those scant numbers work, how they fit into the 2 equations, you go over enough of these, and you should be able to, once you're well practiced, you should be able to set up the function that needs to be minimized in maybe a minute, because there are really just 3 numbers in these. So let's see if we can make this one go. Again, I'm going to attack this one the same way I did the previous. I'm going to look at the numbers I know versus the numbers I don't know. Well, we need to make a total of 640,000 boxes. So I'm going to put that in a little square up here just so I remember. So let's see if we can come up with the annual setup costs first. So every time we go to manufacture this type of jars, it takes us $2,000 in downtime. We still have to pay the folks to do the work. We have to move stuff around. We're not producing anything. It's a strict cost of $2,000. All right. So now let's consider part A. If we manufacture 80,000 boxes every time we set up the production run, the first thing we were going to want to do is, okay, if we have 80,000 boxes per production run, I'm going to set that up, and then I'm going to work through to part C as well, and I'm going to leave part B out and let you figure that one out. So on to part C. If we have X boxes per production run, this is the number of boxes we need to produce. So we have to figure out how many times a year we're going to have to set up the machinery to do that. So let's see, 64. I'll do this a little higher on the screen so I don't run out of room. If I have 640,000 boxes that I need to manufacture, and I'm going to do these at a lot of 80,000 boxes per run, notice that the zeros all cancel out. It looks like that's what, eight total runs. And notice also here I have boxes divided by boxes per run. Dividing by a fraction is multiplying by the reciprocal, boxes times runs per box. And it's important to understand how these unit cancellation things work, especially when we get into the material after the next test when we're talking about antiderivatives and definite integrals. So here the box units totally cancel, and we are just left with the number of runs. This is 8 production runs. Okay. So I'm going to do the same thing over here. If I have X boxes per production run, well, then it will take me 640,000 boxes divided by X boxes per run. That's the number of runs it's going to take. Notice when X is 80,000, that number comes out to be 8. So now we need the cost of the setup. Okay. 8 runs, I think each one was $2,000, yes. So we have 8 runs multiplied by $2,000 per run. So 8 runs, $2,000 per run. The run units cancel. $16,000. Okay. How to calculate the setup cost for that? Well, it's the number of runs, which we have right here, multiplied by 2,000 per run. So 640,000 over X multiplied by 2,000. If you wanted to, you could multiply that out and put a dot here instead of an X. A little more clear. If you wanted to, you could multiply all that together in the numerator. I'll see if I can do it. 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. And 2 times 64 is 128. Here you go, 1,280,000,000. That's the number of dollars that it's going to cost us for the setup cost. Again, if you substitute in X equal to 80,000 here, you should find that that is again the 16,000 that we had before. Setup cost, we have to come up with the annual storage cost. Again, back to part A. Storage cost, if we order 80,000 boxes a run, here's how our inventory is going to look. We'll have 80,000 boxes in storage. We'll sell them out in 1/8 of a year. I guess there's going to be 8 runs in a year. So 1/8 of a year later, they'll be sold out. We load up the machinery again. Build them, load up the machinery again, and we continue this on 8 times. Now, we're not going to have to pay for storage for 80,000 boxes because we don't have 80,000 boxes. On average, we only have 40,000 boxes. Right? So some of the time, there's not any at all in storage, and we'd be silly to pay storage for that. So assuming that these things go off the shelves in a fairly linear manner, what we will have for storage cost will be 1/2 of the 80,000. So that many boxes, and we're going to multiply that by whatever it cost per box. Was $10 per box. So it's this many boxes times $10 per box. So that would, yeah, I'm sorry. Put the dollar sign there. $10 per box. Box units cancel. 1/2 times 80,000 times 10. I guess that's what, 5 times 80,000. That would be 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4. Yeah, looks like that would be $400,000. Okay, storage costs are eating us alive in that case. It's way more expensive than the setup cost. Okay. So how did I calculate the storage cost with a production run that I knew? I took 1/2 of that size of the production run and multiplied it by the storage cost per box. I'll do exactly the same thing over here. X boxes per production run, 1/2 times however many boxes I have in production run, multiplied by $10 per box. Simplifying that, it's 5X. So one more time, I want to make sure I've done this right. I'm going to verify that this is the correct number by plugging in 80,000 here for X and seeing if it brings me back to the number that I knew I should get. So there we have it. There we have it set up. That's the setup for question number 6. Now on to form the variable cost function. Well, there's only 2 things here that make our cost vary. How many times we have to set up the machinery, and how many times we have to and how much we have for storage costs. Everything else is pretty standard. It's going to cost us so many dollars to manufacture these, regardless of when we're doing it. So those those costs tend to be stable. The things that vary are these 2 costs. the setup, the machinery cost, and the storage cost. It's that combined cost, the sum of those two, that we want to make as small as possible. So I'm going to come up with the C of x function. This is the function that we will want to minimize, and it'll be the total of those two. So let's see if I can keep my numbers straight here. And off in the corner, I'm going to remember what my x stands for. Always important to know what our variable is. So there's the cost function, and that's the one I want to try to minimize. Since the algebra here is slightly different than the previous ones, I'm going to go through this in its entirety as well. If you remember, well, I'm going to have you help me go through with it, I guess. So our first step is always to see if this function has a minimum value someplace in the domain. I didn't mention the domain here. I'm not sure if we have a number that for x that could work. I mean, we could do it once a year. We could do it 100 times a year. Or we could do 1 box, I guess, per production run. We could do 100 boxes per production run. We could do 1,000. I'm not sure if there's really a great domain here. I guess x has to be bigger than 0. X has to be 1 or more, I guess. We can't do a half a box of jars of production run. I don't know. But I'm hoping that the cost function looks something like this, and it has a minimum value for those two combined costs. Let's see if it does. If we're going to do that, we want to find that critical point, and to find the critical point, we take the first derivative and set it equal to 0. So spend a little time here. Take the first derivative of this and let me know what you get. What exactly is the first derivative for this function? A little maybe quick reminder is let's rewrite that one first so that we don't have to use the quotient rule. So let's do a quick rewrite step on that, then take the derivative, and if you could, then bring me back the first derivative in a form without any negative exponents. I'll do the easy part. I know the derivative of 5x added on is simply 5. What do you get for the derivative of this part? Good. So negative 128000000 over x squared. And if we're going to find the critical point, we want to find out where the slope of this graph, the slope of this graph is 0. So we'll set this equal to 0. Now, I talked about this when I set up the first problem on the video I recorded that covers this stuff. I always like working with positive numbers, and since this is negative, I find it easier to move this number to the other side by adding that to both sides. So we'd have a 128000000 over x squared is equal to 5. 2 steps of algebra left. Let's multiply both sides of this function by x squared. That way we've eliminated the fractions. I guess 3 steps of algebra left. Divide by 5 and then take the square root. So do those last steps for me. I don't have the answer key up here. Tell me what you get for the number x once you divide both sides by 5 and then take the square root. Okay, okay, 16,000, all right. So I kept my identifier for X there, so I did forget what it was. X is 16,000 boxes per run. Now, before I go and figure out all the details here, I'm going to sort of show you a quick look behind the scenes as to where all the numbers came from. There were just 3 numbers given in the problem, and here's how my C of X turned out. It was 2,000 times 640,000 over X plus 1/2 times 10 times X. Those were the 3 numbers that were given in the problem. So once you see how these problems work and you can make sense of those, the setup is just so fast. So we have 16,000 for our X. So we have 16,000 boxes per production run. Thanks, Devin. That looks really good. Now let's go back and finish out everything that we need to know, the number of boxes we should do. So that's part E. On to part F, using the second derivative. Well, we had the first derivative was negative 128. Oh yeah, all those zeros. X to the minus 2 plus 5. There's our first derivative. Our second derivative of X, bring that down, double it. It looks like that would be 256,000,000,000 over X cubed. Bring the power down, multiply those two together, reduce the power by 1, which makes that X to the minus 3. There it is. Now, when I plug in this critical point, when I evaluate the second derivative at this critical point, the only thing I care about is whether I get a positive number or a negative number. So C double prime of 16,000 is 256,000,000,000 over 16 followed by 3 zeros cubed. I'm really not interested in the exact value of that number in this case. I just want to note that since it's a positive number divided by another positive number, I know that that result is positive. And since the second derivative is positive, I have a graph that's concave up right around that critical point. And I have indeed found a minimum value. So now let's see if we can do the roundup. That question at the end. How many boxes should we produce each production run? Oh, that many. How many production runs are we going to have to run each year? Well, let me think about that. We needed 640,000 boxes. So 640,000 boxes divided by 16,000 boxes per production run. That's 640 divided by 16. At 40? I think it's 40, huh? Yep. So it looks like we should do 40 production runs. This is really the 2 most important pieces of information as far as talking to the manufacturer, right? How many should we do each run? I suppose is the most important one. So that would result in 40 production runs. What would the storage cost and the setup cost be? Well, thinking back, let's see. I could put it. I guess I could put my 16,000 right back in there, or I could figure it in a more rational way. It's $2,000 each time I set up the production. So 2,000 multiplied by 40 production runs. That's 8 followed by 1, 2, 3, 4 zeros. Looks like that's $80,000. Okay. And then I'm going to also calculate the storage cost. So this is the setup cost. Setup cost. And here's my storage cost. Storage cost is given by that. I have 16,000 boxes per run, 16,000 times 5. Look at that. It's the same darn number. Huh. And if you add those two costs together, it should be significantly less than what you got in Part A. It should be a little bit less than what you got in Part B. Okay. Yep, 16,000, we have it. So now I can wrap everything up. What are the setup costs? $80,000. What are the storage costs? The same number, $80,000. That combined cost at $160,000 is the minimum cost I can find for this type of problem. So we practice on these a little bit. If I'm not mistaken, I think I had 3 of these on the MyLab Math assignment. You can always go in on the gradebook section of MyLab Math and rework problems over and over again. So it'll give you slightly different numbers each time. But as you get used to these should go as smoothly as anything else. Again, there's just 3 numbers involved. If you can figure out where those 3 numbers go and why they go there, then this problem is pretty doable. Do I have any more questions over activity number 16? Sometimes the bigger challenge on a problem like the one I just erased is to make sense of all of those pieces of information. How many boxes per production run? What would the storage cost be? How many times do I have to set up the machinery? If you can see how all those pieces work together, then these become easier and easier. Go over number 4, sure, Sarah? Number 4, graph the critical inflection points. Okay, so in order for me to do number 4, I guess I'm going to have to start with number 3, huh? So we want to make 2 well-labeled charts for that function. It's a 3rd order polynomial with a positive coefficient. So I have an idea that this graph has to look probably something like that, knowing what I know about 3rd order polynomial graphs with positive coefficients. Let's see if I can find critical points and an inflection point in place on there. And I'm guessing I can, because otherwise I probably wouldn't have written this problem for part 2. All right, first thing to do, find the critical points. Critical points are when the first derivative is equal to 0. I'm going to write up the first derivative right away. 3x squared minus 12x. Oh, that wasn't too bad. I'll set that equal to 0 and solve. This is a factorable one, simply factorable because it only has 2 terms and there's a common x. If I factor out a 3x, it's 3x times x minus 4. And my quadratic equation is a breeze to solve. X equals 0 and x equal to 4. This is very similar to one of the questions I had on the algebra preview activities. Students struggled like crazy with this one in the past. I'm hoping that that's paying a little dividends here. So those are my 2 critical points. At x equals 0, the graph is absolutely flat, and at x equal to 4, the slope is 0 as at x equal to 4 as well. Now I do want to find those 2 points because I'm eventually going to have to graph them on the graph. So I'm going to go back to my original function. I'm probably only going to plot 3 points on this graph. I'm going to plot the 2 critical points and the inflection point. I'm going to calculate g of 0. That one I can do mentally, and calculate g of 4. I could probably do that as well. Why doesn't someone in this class tell me what g of 4 is? That's probably maybe just a little bit beyond my my mental abilities. I didn't bring a calculator up here. G of 0 is a piece of cake. G of 0 is equal to -5. So I'm off in the corner here. I'm going to remember I have critical points. One of them is 0, -5. One of them is 4, comma, whatever you tell me it is. These are the CPs. So plugging 4 into my function, what do I get? No, we don't want to plug this into the first derivative. The first derivative won't give us points on the graph. We want to find the points where the first derivative just tells us the slope. Yeah, so if you plug 4 in here, you better get 0. We know the slope is 0. We need 3 points on the graph. In order to get points on the graph, we have to go back to the original function. And mentally, it's looking to me like maybe it's negative 37, but I'm not convinced. Yep, okay. If someone else got something different from that, let me know, but that's mentally what I got, and that's what Sarah just indicated as well. So there's the 2 critical points that'll go on the graph. Now, before I find the inflection point, I'm going to make my first chart. And these charts tend to be a little lacking unless I go over this time and time again. So here we go. Intervals. Okay, so we need all the numbers before the first critical point, negative infinity to 0. All the numbers between the critical points, 0 to 4. And then all the numbers after the last critical point, any number from 4 to infinity. What I'm going to do then is select some test point in each of those intervals. I'm going to choose the easiest one possible. There I'll select a -1, here a +1, and here a 5. Now this is where students sometimes get a little bit lost. This is the value of the first derivative of g prime in this case, since it's a g function. I want to know on this graph whether the function is increasing or decreasing. That's what the first derivative tells me. So now I'm going to plug these values into the first derivative. And it doesn't matter which form you use. I prefer the factored form. Makes the multiplication a little easier, but use either form you wish. So if I plug a -1 in here, that's -3 times -5, that's a +15. If I plug a 1 in here, it's 3 times a -3, that's a -9. If I plug a 5 in there, I get 15 times 1, that's a +15. Now, I'm not so concerned that with what those values are. The slope at 0 is 15, okay. I'm sorry, the slope at -1 is 15, that's good. The slope at 1 is -9, that's fine. The slope at 5 is 15, that's fine. What I really am interested in is what the sign of each of those are. So here's my behavior of the graph. And since the value of the first derivative is positive, I know that this function is increasing. And there's the first of the 2 charts. So when I go to graph this, I'm going to keep this cemented in the back of my mind. I have a function that's increasing, decreasing, and increasing. It stops increasing at 4, and it stops decreasing at, it stops increasing at 0, and it starts increasing again at 4. So I have a decent idea what the shape is going to be. Okay. All right. So the -37 has been confirmed. Thank you. That's the first chart. The first chart tells me whether it's going up or down. The second chart I'm going to use is going to help me with the shape of this one. And since we've done a number of third-order polynomials, this one should be probably familiar as far as the shape is concerned. But I like to just verify everything and make sure everyone understands how it works by using the second derivative. Second derivative here is 6x minus 12. Again, I want to set that equal to 0. At 0, the graph has no concavity at all. It's perfectly straight. Solving this is simple. X is equal to 2. So those are my 2 critical points. This point here, There we go. This point here, where x is equal to 2, that's my inflection point. That's where it changes concavity from concave one way to concave the other. We'll figure out those details in just a second. So let's figure out what this point is on the graph. Again, we need 3 points on the graph. Those get substituted in the original. This one I think I can do. It's going to be 8 minus 24 minus 5. 8 minus 24 is negative 16. Negative 16 minus 5 is negative 21. If someone gets something different than that, give me a quick note on the chat box, but I'm 90% sure that's right. Okay. So in each of these points gets plotted. Each of those points are points on the graph. Each of those points I calculated by plugging them into the original function. Now the second chart. Intervals. Test point. Value of, in this case, G double prime. And behavior. Well, we only had one case here where we had an inflection point right at x equal to 2. So this chart will have one fewer column. We're going to look for all numbers before my inflection point, negative infinity to 2, and then all numbers after my inflection point from 2 to infinity. Choose a test point. I like 0 if it's available, and it is. 0 and 3 will be the two test points I use. Plugging these into the first derivative, this one is negative 12. Plugging a 3 in there, I get 18 minus 12, I get a positive 6. Again, these values aren't really all that important. This is how quickly the slope is changing. It's changing at negative 12 units per unit. But what's more important is the sign of that one. And since that's a negative, I know that this section of the graph is concave down. And since the second part is positive, I know that that is concave up. So now we're ready to draw the graph. I'm going to use those 3 points. I'm going to use from my memory banks what the graph did as far as increasing and decreasing, and then concave up and concave down. So I'm going to lose all of this. And off to the graph. See, everything is below 0. Most of the important stuff is off to the right. So when I go to graph this, I'll probably make it look like this. On to 4. So let's see, 1, 2, 3, 4, 5, 6, maybe. Negative 37s as far as they have to go. How about negative 5, 10, 15, 20, 25, 30, 35, 40. There's negative 40. Let's plot the 3 points. 0, negative 5, point on the graph. 2, negative 21. 2, negative 21, 5, 10, 15, 20, 2, negative 21, right about there. Always a danger when drawing without grids. And then 4, negative 37, 4, negative 37, yeah, right about there. So what I remember from the first chart is this graph was increasing, decreasing, and then increasing. What I remember from the second graph is it was concave down until I got here, and then concave up the rest of the way. So here goes. And I like to sort of do dotted lines here until I feel really confident about my curve. You know, that's pretty good. That's concave down, okay. Now I have to switch concavity. I have to start making it concave up. Maybe make it concave up a little sooner. It's got to come down, hit that point. There we go. And from that point on, we can slap arrows on the end. We know nothing else special happens. We know it doesn't loop back on itself ever thereafter because the function continues to be increasing, continues to be concave up. We know nothing happens beyond this side either because we know the function continues to be increasing and continues to be concave down. So we have absolutely everything that's of importance on this graph by just plotting those 3 points. You have negative 37, good. Can I explain the test points? How do you choose them? Sure. The test points I choose are just numbers in the interval. So if I go back to the second derivative chart, so the test point I'm going to choose has to be any number that's in that first interval. So I choose any number, and it's regardless of choice. If 0 is available, I like to select it, so I'm going to select 0. Okay. So now I need any number from 10 to infinity. Well, I'm thinking, what's going to be the easiest for me to evaluate in the second derivative? I'm not going to choose 10,000 because it's going to be difficult. I'll just let x equal to 3. So this 3 is in that interval, 0 is in that interval. And again, it doesn't really matter how you select them. They just have to make sure that they are in that interval. Welcome. Sarah, you had a different question you wanted to ask me, right? Yeah, it's number 5. Okay, so I can certainly go over number 5 as well. Okay. So on number 5, I'm going to again treat part A and part C, sort of mirror them as I go along. In both cases, I have a sheet of cardboard. Fold up the corners. So typically in box construction, you put just a fancy little fold on the corners. You don't cut the tabs out. But if you look at any box that you get from a shirt box, for example, you see the funky little folds, nice little rectangular corners that are folded in. But in this case, we're going to cut a piece of stock out. So this one turns out to be a square in the beginning, 16 by 16. I'm going to make my picture look a little more squarish. So if I cut these corners out, then what I would do is fold along these dotted lines and come up with a 3-dimensional box. And I'll do my best to draw a 3-dimensional box in 2 dimensions. I should have brought my cardboard stock up with me. Of course, you're going to be viewing this on the screen. I guess it would make a bit of difference, would it? I can turn it, maybe give you a little better idea of 3 dimensions. Maybe I'll do that in my 345 class. I'll bring up a piece of card stock. Feel free to view in again. So if we cut a 2-inch corner out of each of these pieces, then the height is going to be 2 inches. Okay? Folding up on that tab, folding up on that tab. If I do the same thing with this box with an unknown tab cut up, then each of these, or the height of that box is going to be X inches. Back to part A. What will the volume of the box hold? Well, remember that this was 16 both across the side and across the top. So if I cut a 2-inch corner out of here and a 2-inch corner out of here, the dimensions that are left for the bottom of the box it's no longer going to be 16. I'm going to lose 2 inches there, 2 inches there. It's going to be 16 minus 2 times 2, 16 minus 4. That's only going to be 12 inches across. Same thing for the other dimension. It starts 16 here. I lose 2 inches on the top. I lose 2 inches on the bottom. So that dimension from dotted line to dotted line, again, would have been 12. That's in the case if I knew exactly what size the corner to bend up, to cut out, and to bend up along the folds. Now on my case where I don't know how big that's going to be, well, again, I'm starting with a 16-inch piece across here. I'm losing X on this side, so that part right there is X. I'm losing X on this side as well, so I lose an X on both sides. So 16 minus 2X should be both the length, and since this started out to be a square, 16 minus 2X is that side as well. Now, here's where I want to make sure that all of my dimensions make perfect sense. Folding that flat is going to be 16 by 16. Yeah, folding this flat, if I if I add double this to this, right, I should get 16. If I add double this to this, I get 16, okay. If I allow X to equal 2, these two should mirror each other perfectly. So allow X to equal to 2, that's where that 2 comes from. Allow X to equal to 2, this is 16 minus 4 is 12. 16 minus 4 is 12. So now I'm sure that that looks exactly right. I am confident that I have my dimensions for the length, the width, and the height correct. Now volume is going to be the length times the width times the height. 2 times 12 times 12. Volume of this particular box looks like it's 48 cubic something or another's. What were my units? Inches, cubic inches. My volume of this box, I'm going to use the same formula, the length times the width times the height. Volume is going to be X times 16 minus 2X times 16 minus 2X. So moving forward then, let's see if we can maximize the volume of that box. Well, we're going to have to figure out what the domain is. We don't want to put some X in there that makes no sense. First off, X has to be bigger than 0. We can't cut nothing out. It's not going to hold any volume if we cut nothing out and fold nothing up. But we also have limits on this. I cannot, since this is a total of 16, right? I can't cut a corner bigger than 8 out. If I try to cut an 8-inch corner and an 8-inch corner out of that, I'm cutting really right down the middle and there's nothing left. I could certainly cut a 7-inch out there and a 7-inch out there. That'd leave 2 in the middle, 7.5 in the top, 7.5 in the bottom. That would leave an inch in the middle. But I cannot cut 8 out. So my domain on this one has to be between 0 and 8. Otherwise, I cannot get any volume whatsoever. There's the working domain. Call that V of X. I'll go back to the rules stated in the problem. That's V of X. That's the function that I wish to maximize. I notice that's a third order polynomial. So I'm having an idea about what the shape of this graph is. Not that it's important, but there it is. Now we're going to find the dimensions that give the maximum volume. All right. So there's our function. There's our domain. I would like someone, if they would be so kind, to multiply all of this together and give me one expression without any parentheses. So we're going to unfactor it. We're going to what's known as simplify that set of factors. Tell me what V of X should be. Let's see what we got here. So we have a 4x cubed minus 64x squared plus 256x. Yeah, that looks good. All right, so we want to maximize this function on that interval from 0 to 8. Let's take our first derivative. Easy enough, 12x squared minus 128x plus 256. As always, we're going to look for the critical points. We're especially going to be interested in the critical point that falls between 0 and 8. Critical points are where the first derivative is equal to 0. Boy, we've seen that enough times, haven't we, in the last couple of days? Now we have a quadratic to solve. I don't like the chances of this factoring a whole bunch. I do think that there's some factoring we could do if we wanted to. We could factor out, let's see, that doesn't have an 8 in it. I guess the best thing we could do maybe is factor out a 4. Make this be a 3x squared. Not that this is important, I'm going to do it and explain why in a second. Plus 32x plus 6, 24, 16, 64. Again, I'm not precisely sure how this would factor or if it would factor. So I'm going to rely on the quadratic formula. X equals. Now here's where I sort of like factoring the 4 out. Again, it's not necessary. X is equal to, according to the quadratic formula, 32 plus or minus the square root of 32 squared minus 4 times 3 times 64. The whole thing divided by 2 times 3. So negative b plus or minus square root of b squared minus 4ac over 2a. The reason I kind of prefer this is the numbers are a little more reasonable. If I use the top one, it would have been 128 plus or minus 128 squared minus 4 times 12 times 256 divided by 2 times 12. So it makes it a little easier as far as messing around with the numbers in the quadratic formula go. So someone, if they'd be so kind, find what that is equal to. And let's round it to the nearest 1/10, please. Oh, you were able to factor it. Excellent. Yeah, I like it. Look at that. It did factor. Incredible. All right. So it looks like if you solve this correctly, you should get 2 solutions. One of them should be x is equal to 8, and the other one is x is equal to 8 over 3, or 2.67, I guess, huh? Yep, 8/3 and 8, yep. Now this one we can knock out. There's no way that we're going to get a maximum volume at x equal to 8. X equal to 8 doesn't give us any volume whatsoever. So that's not in the domain. The only one that is in the domain is 8/3. Okay. And I want to be precise on this one. I want to make sure that that's actually going to give us the maximum value. I'm going to check to make sure it gives us the maximum value to make sure that the graph is concave down when x is equal to 8/3. So I'm going to apply the second derivative test here just to ensure that I found a maximum value. V double prime of x is 24x minus 128. And if I plug 8/3 in here, I get 64 minus 128, that's equal to a negative 64. So when I calculate V double prime of 8/3, I get 64 minus 128, and sure enough, that is negative. Therefore, the function is concave down. It's concave down with x equal to 8/3. And I found the maximum value for the function in that interval. All right, so now let's wrap things up. 8/3, I guess maybe I'll round this to the nearest hundred. 8/3 is going to be 2.67 inches. So now I know the corner that I should cut out of the box, 2.67 inches. So let's see if I can figure out what the dimensions on this are going to be. That's got to be 2.67. The other two sides started at 16, but I have to fold a 2.67 off of each side. 2.67 times 2 is 5.34. Okay. 16 minus 5.34, looks like those other two sides should be 10.66. So that would be the dimensions that would give me the maximum volume. And if you multiply all three of those together, that should give you the maximum volume, as long as my arithmetic that I did mentally holds up. Okay. Any more questions on this one? Any corrections on this one, or any other comments that you have as far as this activity or anything else is concerned? 10.66 is not the maximum area or the maximum volume. Oh, did I have a maximum area on here? Oh, there's a big misprint. Whew. Okay, so there's no maximum area on this. That should not have been part of this discussion at all. We have no area here that we are trying to maximize at all. So part F should be find the dimension that has the maximum volume. Dimension of the box that has the maximum volume. There is no maximum area. There's the area that we started with was that area, that piece of cardboard. There's no area here to be concerned with. We just want the max volume. So the max volume we'll get by taking 2.67 times 10.66 times 10.66. So whatever that comes out to be, I know those are the dimensions that's going to produce the max volume. That should be bigger than what I had in the very first problem, where I had the 2 inches folded up on each side. Nice. Devin, I'm a little confused. Is the numerator x numerator of what? Thanks for alerting me. That's a misprint that just keeps going from semester to semester. I'll make sure I mention that at the start of the problem. If I have the same thing coming up. Oh, this x squared down here is just multiplying by 2. if I'm folding up a section that's 2.67 on each corner and multiplying that by 2, 5.34. So I'm losing 5.34 off the base of each side because I'm folding up at 2.67 on each side. So 16 minus 2.5 or 5.34 shows me what the length of each of the dimensions of each of the base pieces are, both the length and the width. Okay, so that wasn't an x squared, that was a times 2. I'm multiplying this times 2. Okay, so the 2.67 gets cut off both sides before I do the fold up. 2.67 out of that corner, 2.67 out of that corner. That leaves me 10.66 on the folds. Yeah. So that was a times 2. Yeah. So there's my attempt at messy mental math. See what we've covered on this one. We did 3 and 4 all the way through. We did 5 all the way through. We did 1 all the way through. We did 6 all the way through. We did 7 all the way through. Yeah. So we've covered just about everything. Yeah, you weren't the only one, Devin. It did look like an x squared. Anything else? Okay, well, it's just, yeah. I'll be back at 3:45. I'm probably going to end this stream and then start a new one at 3:45. That way there's not 15 minutes of dead air. So look for that web address if you're interested in seeing this again or having some more questions for me. Log in again. One more time, this will be available. It's always available at the same web address, so you can go back and review this if you like. My kitty made a nice entrance in the beginning. If you get to see the most beautiful cat in the world, she resides right here in this house, and she was anxious to get on camera at the very beginning. So if you're interested in seeing the most beautiful cat in the world, play this over from the start and you get to meet my Squeaky. And you're welcome, Sarah. Glad that you could join us and glad everyone could join us. And I hope this made sense. Talk to you next time.